In this video, I'm going to show you how to run a stress-based fatigue life prediction in Fe-safe using stress result from Abaqus. But here's the interesting part. I also cross-checked the results using the standard fatigue life formula you'll find in engineering textbooks. And the prediction was surprisingly accurate. We'll go through the full workflow from setting up your simulation in Abaqus, importing the results into Fe-safe, and analyzing the fatigue life output. If you've never worked with Fe-safe before, this is a great place to start. Let's get into it. Before we start, I want to talk about the stress-based fatigue simulation with Fe-safe. It's pretty vital to know how it's being done, because any value you give to the software, it gives you a contour or a life which might not be accurate. It's vital to know the theory behind it so you can do that more accurately. Here how it goes. This is the SN curve of a material, and the slope of the SN curve would be B, which is the fatigue strength exponent. We have sigma F here, which is the fatigue strength coefficient. Using the Basquine's equation, we have delta sigma, which is the fatigue range. It can be calculated from the amplitude of stress sigma A, and we have sigma prime F to NF to the power of the B, and NF is the cycle to failure. So what does Fe-safe do? When you import your finite element model, Fe-safe take stress from your results. This stress is maximum principal stress. Then it calculates the delta sigma, and using the fatigue properties such as sigma prime F and B, it calculates the NF and gives you the life. Now let's go to Abaqus to see the model we created. We simulated this model before and explained everything in details. I put the link on top right here and in the pinned comment down below. So make sure to view the video before you start this one. So here we have the properties. This is the steel. We only have the elastic materials here. This is the Young's modulus and Poisson's ratio. Then this is the step. We have the step, time period is 1, and these are the number of increments and increment size. And in the boundary condition and loading, we fixed one side and pulled the other side. We create a displacement rotation on this one. And one thing which is different from the video you're going to see is we had this value for 1000 megapascal, but that is too much for the fatigue, and I reduced that to negative 100 megapascal. So this is the first change we've made. And also, before submitting the job, you have to make sure to go to the tools, and from set manager you create a set, put it on element, continue, and select everything, and done, because we're going to use that for Fe-safe to analyze. Okay, let's go to Fe-safe to start the fatigue simulation. So let's open Fe-safe. This is Fe-safe. We put a name for this project, say SN fully reversed, and nice time to import the model. So you can either go from here, file, and from FEA solution, open finite element model, or you can right click here and say open finite element model, which is the shortcut and way easier. So the job we had here is played with a hole. Do you want to pre-scan? Of course, yes. This is elemental, stress strain, and make sure to check the last increment only, because the step has a couple of increments and we want only finite result. So these are selected and click on OK. Here is pretty important. If we go to Abaqus to see the result, let's go here and see the job. You see here we have 2.50 to the power of 2, which is megapascal. So here in Fe-safe, this guy must be megapascal. If we put that pascal or kilopascal or anything like that, it will ruin the simulation and give you wrong answers. Okay, megapascal, strain, degree centigrade, which we don't need, and the forces are Newton, and it's millimetric. Click on OK, click on yes. we send everything here. It says unused group, and we have the analysis group here. We only send all, which is the set we created, to this one. So we only want to analyze this group. Click on OK. Here we have all and default, so you right click on default and edit, and click on do not analyze. So we don't need this default and we only need this one. Right click on surface and put it on hold, so we don't want to analyze the surface only, we want to have the whole bulk. And it's time to select the material. Here we go to the system and let's select SAE 1040. We only left click on it, and here we right click on the material and edit. It automatically recognizes the SAE 1040 and let's say yes, and the material is assigned. Now let's edit the algorithm. Select an algorithm here, and from biaxial stress, normal stress, we don't need Goodman or Gerber here because we have a fully reversed model and the sigma m is 0, so it doesn't matter to use Goodman, Gerber or none, it gives you the same result. Okay, now let's go to the loading setting. Here we need to clear the default load, so right click on here and say clear all loading. Now the loads are clear. We need to generate the signal or the load history. We go to the generation, signal generation, sine wave, put this one on 4 because we want it to be the fully reversed. 1, the sample frequency is 4, amplitude is 1, and the phase is 0. As we click on OK, we see there's a file generated here. So let's right click on this one and click on plot. As you see here, we have a fully reversed load. Okay, we close this one. We need to select the loading data, so just click on the stress, and here this one is selected also, a load data set, and OK. And now we have the stress data set. If you select the strain, it would be under the strain. So everything looks good. Okay, now it's time to do the analysis. But before we analyze the data, I want to ask you a favor. If you enjoyed this video so far, please share your feedback with me in the comments down below. It's totally free for you, but it motivates me to create more videos like this. Click on this one, click on OK, continue. And as you see here, the life is 206,000 cycle to failure, and we can see the filter summary by group, or we can open the results file. Let's open the ODB file first. This is the ODB file, but is the fatigue life file, and as you see here, it only gives us the log file. We can have the damage as well, but we have to request that before the analysis. Okay, this shows the fatigue life, but it's the log life. So if you want to know the exact number of cycle to failure, you need to do a simple calculation, which means 10 to the power of this number. So here we have the kernel of Abaqus. If we want to do the calculation, let's say 10 to the power of 5.316, and it gives us that value. Now, how do we know that this number is accurate or not? Let's jump back to the PowerPoint files. I extracted all the parameters from the software. If we go to the Fe-safe, this is SAE 1040. If I click on this one and scroll down, I can see here this is the B, and here we have the S prime F or sigma prime F. So this is the material properties. And here we have the loading type. The loading type is fully reversed. It means we have plus sigma max and minus sigma max. And if we go to the Abaqus file, and here if you see show location, or here you can see this is the maximum principal stress we have. So let's go back here. We have the maximum stress, and let's see the calculations. If we have a fully reversed load, we have sigma max minus sigma min and we have the sigma A. So the sigma A would be calculated as 250.46 megapascal, which is the same as the stress we have. In the next step, we have the Basquine's equation. If we arrange that to solve the n, this is the formula we are using. And here we have the 250, and this is the sigma prime f and b, and the calculated life would be 213,000, which is fairly close to that number we obtained from the software. If you enjoyed this video, subscribe to the channel to see more videos like this, and click on the video on screen before it ends. Stay tuned.